Picture this extraordinary feat of human ingenuity. You're soaring through a vast metropolis at speeds that break the sound barrier, all while attempting to create an impossibly precise three-dimensional map of every building, street, and structure below. Now multiply this already mind-bending challenge by billions, and you'll begin to grasp the monumental achievement of the Gaia Space Observatory. This remarkable mission stretches far beyond the confines of any earthly city. It's undertaking the most ambitious cartographic journey in human history, mapping our entire Milky Way galaxy in stunning three-dimensional detail. As we delve into this fascinating exploration of space, we're witnessing a revolution in our understanding of the cosmic neighborhood we call home. Through the eyes of a single spacecraft, we're uncovering the secrets of ancient stellar collisions that shaped our galaxy, discovering hidden patterns in the cosmic dance of stars, and piecing together the intricate puzzle of our galactic past. But this isn't just about looking backward. Gaia's unprecedented mapping capabilities are helping us peer into the future of our galaxy, revealing how our cosmic home will evolve over millions of years. The implications of this mission are truly staggering. Every data point Gaia collects adds another piece to our understanding of the Milky Way's structure, its formation, and its destiny. We're not just passive observers in this cosmic journey. We're active explorers, using cutting-edge technology to unravel the mysteries that have captivated astronomers for centuries. As we embark on this exploration together, we invite you to join our growing community of space enthusiasts who share our passion for understanding the universe. By subscribing, you'll become part of a collective journey through space and time as we uncover the secrets hidden in the stars above. This story of discovery represents humanity's endless quest to understand our place in the cosmos. It's a testament to our species' ingenuity, our relentless curiosity, and our ability to push the boundaries of what's possible. Together, we'll explore how this revolutionary mission is transforming our understanding of the galaxy we call home. One star at a time, the human quest to understand our place among the stars stretches back to the very dawn of civilization. Ancient astronomers, armed with nothing more than their eyes and primitive instruments, began the painstaking process of cataloging the heavens. The Babylonians, as early as 1600 BCE, meticulously recorded the positions of stars on clay tablets, creating the first known star catalogues. This tradition was carried forward by the Greeks, with Hipparchus of Nicaea creating what is considered the first comprehensive star catalogue in the Western world around 129 BCE, documenting the positions of roughly 850 stars. Moving through history, Persian astronomers in the Islamic Golden Age made remarkable contributions. Al-Sufi's Book of Fixed Stars, from 964 CE, provided unprecedented detailed observations of the night sky, while Ulugh Beg's star catalogue from the 15th century achieved remarkable accuracy using only naked eye observations and sophisticated mathematical calculations. The invention of the telescope in the early 17th century revolutionized our understanding of the galaxy. Galileo Galilei's observations revealed that the Milky Way's ghostly band across the night sky was actually composed of countless individual stars. By the 18th century, William Herschel attempted the first systematic survey of the galaxy's structure, though his model proved incorrect in placing the Sun near the center of the Milky Way. The 20th century brought dramatic advances in our understanding. Harlow Shapley's work with globular clusters in the 1910s helped establish the true size of our galaxy and the Sun's position within it. The development of radio astronomy in the 1950s and 60s revealed the spiral structure of the Milky Way, hidden from optical telescopes by intervening dust. A quantum leap forward came with the European Space Agency's Hipparcos mission, launched in 1989. This pioneering space telescope measured the positions and parallaxes of more than 100,000 stars with unprecedented precision, creating the first space-based catalogue of stellar positions. Hipparchus achieved accuracies of about 1 millisecond for the brightest stars, a remarkable achievement that seemed impossible just decades earlier. Yet despite these monumental achievements spanning millennia of human observation and innovation, they all pale in comparison to what the Gaia mission is now accomplishing. Where Hipparchus measured thousands of stars, Gaia is mapping billions. Where previous catalogues achieved precision measured in arcseconds or milliarcseconds, Gaia achieves micro-arcsecond precision, equivalent to measuring the width of a human hair from 1,000 kilometers away. This extraordinary leap in capabilities represents not just an incremental improvement, but a fundamental transformation in our ability to understand our cosmic home. We have progressed from ancient astronomers, carefully noting the positions of a few hundred bright stars, to a space observatory automatically measuring the precise positions, distances, motions, and physical properties of nearly 2 billion stars. It's a testament to human ingenuity and our relentless drive to understand our place in the cosmos, representing the culmination of a journey that began when our ancestors first looked up at the night sky and wondered about their place among the stars. The Gaia Space Observatory stands as one of the most sophisticated scientific instruments ever created by humanity. Launched atop a Soyuz frigate rocket from French Guiana on December 19, 2013. This remarkable spacecraft represents the pinnacle of European space engineering. While many might imagine a traditional telescope pointing at distant stars, Gaia operates in a fundamentally different and revolutionary way. At its core, Gaia is a precision-scanning satellite about the size of a small bus, measuring roughly 4.6 meters across when its sunshield is deployed. This distinctive sunshield, resembling a circular brim hat about 10 meters in diameter, plays a crucial role in maintaining the spacecraft's thermal stability, protecting its sensitive instruments from the sun's intense radiation. The entire observatory weighs approximately 2,030 kilograms and operates in a carefully chosen orbit around the Lagrange point L2, located 1.5 million kilometers from Earth in the direction opposite to the Sun. What truly sets Gaia apart is its innovative scanning mechanism. The spacecraft slowly rotates around its axis once every 6 hours, completing a full scan of the sky approximately every 6 months. This constant spinning motion, combined with the spacecraft's orbital movement, allows Gaia to observe each star in its catalogue an average of 70 times over its mission lifetime. This repeated observation is crucial for achieving the mission's extraordinary precision in measuring stellar positions and movements. The heart of Gaia's observational capability lies in its 2 identical telescopes, set at a fixed angle of 106.5 degrees apart. These telescopes share a common focal plane containing the largest digital camera ever flown in space, a remarkable array of 106 CCDs with nearly 1 billion pixels. The telescope's primary mirrors, each measuring 1.45 x 0.5 meters, feed light onto this sophisticated sensor array. The precision of these instruments is nothing short of astounding. They can measure star positions with an accuracy equivalent to spotting a human hair from a distance of 1,000 kilometers. But Gaia's capabilities extend far beyond just position measurements. The spacecraft carries 3 main scientific instruments: the astrometric instrument for precise position measurements, the photometric instrument for determining stellar properties like temperature and composition, and the radial velocity spectrometer for measuring the speeds at which stars are moving toward or away from us. This combination of instruments allows Gaia to create not just a static picture of our galaxy, but a dynamic, 3-dimensional map showing how stars are moving and evolving over time. The spacecraft's thermal control system is equally impressive, maintaining its critical components at a stable temperature of around 110 degrees Celsius. This extreme cooling is essential for the precision of its measurements, as even tiny thermal variations could affect the accuracy of its observations. The entire structure is built with materials carefully chosen for their thermal and mechanical stability, including silicon carbide ceramic for many of its critical components. Operating from its vantage point at L2, Gaia communicates with Earth through a high-capacity digital link, transmitting around 100 gigabytes of raw data every day. This massive data stream is then processed by a dedicated ground segment, involving hundreds of scientists and engineers across Europe, who transform the raw measurements into the precise stellar parameters that astronomers use to study our galaxy. The level of precision achieved by Gaia's instruments and design is transforming our understanding of the Milky Way, creating the most accurate and complete map of our galaxy ever attempted. It's a testament to human ingenuity and our endless quest to understand our place in the cosmos, one star at a time. The sheer scale of Gaia's mission challenges our ability to comprehend its magnitude. When we delve into the numbers behind this extraordinary space observatory, we enter a realm where statistics become almost poetic in their vastness. The mission's scope is so ambitious that it makes previous stellar surveys look like mere glimpses at the night sky. Let's start with the most staggering figure. Gaia is observing nearly 2 billion stars. To put this in perspective, this is roughly equivalent to counting every human on Earth and then doing it again. But Gaia doesn't just count these stars once. It revisits each one approximately 70 times throughout its mission. This repeated observation creates an unprecedented depth of data, allowing astronomers to track subtle changes in stellar positions and brightness over time. The precision of Gaia's measurements defies ordinary comprehension. When astronomers say it can measure the thickness of a coin on the moon from Earth, they're not engaging in hyperbole. The spacecraft can detect angular differences as small as 10 micro-arcseconds, equivalent to measuring the width of a human hair from 1,000 kilometers away. This level of precision would be like being able to measure the growth of a child's fingernail while standing in New York and the child being in Los Angeles. The daily data processing capabilities of Gaia are equally mind-bending. Processing over 500 million measurements every day, the spacecraft generates an astronomical amount of data, quite literally. To put this into perspective, in the time it takes you to blink your eye, approximately 300 milliseconds, Gaia has already observed and measured dozens of stars. Each day's worth of observations contributes to what is becoming the most detailed map of our galaxy ever created. Over its mission lifetime, Gaia will perform about 100 billion positional measurements. This isn't just about quantity. Each measurement includes precise data about a star's position, distance, motion through space, brightness, temperature, and composition. The total amount of data Gaia will collect during its mission would fill more than 1.5 million CD-ROMs. If you were to stack these CDs, they would reach a height of about 1.5 kilometers, taller than many mountains. The computational demands of processing this data are equally impressive. The initial processing of raw data requires a supercomputer performing some 100 trillion calculations. The final catalog data requires over 1,000 terabytes of storage. This is equivalent to about 200,000 DVDs worth of information about our cosmic neighborhood. Perhaps most remarkably, Gaia achieves all of this while spinning in space, completing one rotation every 6 hours and orbiting at Lagrange point L2, some 1.5 million kilometers from Earth. From this distant vantage point, it systematically scans the entire sky, creating what astronomers call a billion-pixel map of our galaxy. When considering the timescale of these observations, another dimension of wonder emerges. In just 1 hour, Gaia collects more detailed information about our galaxy than astronomers managed to gather in the entire 1,000 years before the telescope was invented. Every single day, it adds more precision to our understanding of the Milky Way than what Galileo could have dreamed of achieving in his lifetime. These numbers tell more than just a story of technological achievement. They represent humanity's most ambitious attempt to understand our cosmic home. Each measurement, each data point, each observation adds to our growing picture of the Milky Way, helping us understand not just where stars are today, but how our entire galaxy formed and how it continues to evolve. In the end, these astronomical numbers serve one profound purpose, helping us comprehend our place in the vast cosmic dance of stars that makes up our galaxy. The Gaia mission has fundamentally transformed our understanding of the Milky Way's history and evolution through a series of groundbreaking discoveries. Perhaps most dramatically, Gaia's precise measurements have revealed that our galaxy's past was far more violent and dynamic than previously imagined. By mapping the motions of millions of stars with unprecedented accuracy, Gaia has uncovered evidence of ancient galactic mergers that shaped our cosmic home. One of the most spectacular findings was the discovery of Gaia Enceladus, also known as the Gaia sausage. About 10 billion years ago, this dwarf galaxy, containing billions of stars, collided with our young Milky Way in a cosmic dance that forever altered both galaxies. The collision scattered stars into chaotic orbits, many of which still retain the chemical signatures and motion patterns of their original galaxy. These stars move in elongated orbits that plunge in and out of the Milky Way's disk, creating a sausage-like pattern that gave the ancient galaxy its nickname. Gaia has also detected remarkable phenomena known as stellar tsunamis, massive waves of stars moving coherently through our galaxy. These cosmic waves were likely triggered by past gravitational disturbances, perhaps from passing dwarf galaxies or massive dark matter concentrations. The observatory's precise measurements have revealed these stellar waves, rippling through different parts of the Milky Way's disk, much like ripples on a pond's surface. These discoveries have shown that our galaxy's disk is far more dynamic and responsive to perturbations than previously thought. The mission has unveiled multiple star streams and clusters that bear witness to other ancient galactic mergers. By analyzing the chemical composition, age, and motion of stars, astronomers have identified several distinct populations that originated in other galaxies before being absorbed by the Milky Way. These findings suggest our galaxy grew not just through the gradual accumulation of gas and star formation, but through a series of dramatic collisions and mergers with smaller galaxies. Gaia's observations have also revealed unexpected structures in our galaxy's disk, including a mysterious wave-like pattern that causes it to wiggle and ripple. This peculiar behavior might be evidence of past encounters with satellite galaxies or dark matter substructures. The discovery challenges our previous conception of the Milky Way's disk as a relatively stable, placid structure. The mission has revolutionized our understanding of the Milky Way's spiral arms as well. Rather than being fixed structures, Gaia's data shows they are more dynamic and transient than previously believed, with stars moving in and out of spiral patterns in complex ways. This has forced astronomers to revise their models of how spiral galaxies maintain their characteristic shape over billions of years. Through these discoveries, Gaia has painted a picture of our galaxy as a dynamic, ever-changing system that bears the scars of ancient violent encounters while continuing to evolve through interactions with its satellite galaxies. These findings are not merely academic curiosities. They help us understand how galaxies like our own form and evolve throughout cosmic time, providing crucial insights into the fundamental processes that shape the universe around us. The Gaia mission transcends mere scientific curiosity. It speaks to our deepest human desire to understand our origins and place in the universe. When we look at Gaia's intricate map of billions of stars, we're not just observing distant points of light. We're examining our extended cosmic family, all born from the same galactic cradle that gave rise to our own solar system. Consider this: every atom in our bodies heavier than hydrogen was forged in the hearts of stars that lived and died long before our sun ignited. The iron in our blood, the calcium in our bones, the carbon that forms the basis of life itself, all these elements were created through stellar nucleosynthesis and scattered across space by ancient supernovae. By mapping and studying the chemical compositions of stars across our galaxy, Gaia is effectively tracing the heritage of the very materials that make us human. The mission's precise measurements are helping us understand our own stellar neighborhood in unprecedented detail. For the first time, we can trace the paths of nearby stars backwards and forwards in time, revealing which stars our sun has encountered in the past and which ones it will meet in the future. This cosmic choreography shows us that we're not static observers, but active participants in an endless galactic dance. Through Gaia's eyes, we're discovering that our solar system's story is intimately connected to the larger history of the Milky Way. The data reveals that some of our nearest stellar neighbors may have formed in the same stellar nursery as our sun, making them true stellar siblings. These stars share not just a similar age with our sun, but also nearly identical chemical compositions, a cosmic DNA that links us to a common origin roughly 4.6 billion years ago. The mission is also illuminating the environment that gave birth to our solar system. By identifying stars with similar properties to our sun, we're learning about the conditions that were likely present when Earth and the other planets formed. This knowledge isn't just academically interesting, it helps us understand what makes a stellar system capable of supporting life, potentially guiding future searches for habitable worlds. Perhaps most poignantly, Gaia's map reminds us of our profound connection to the cosmos. When we look at its visualization of the Milky Way, we're not just seeing a scientific dataset, we're seeing our cosmic address in the universe. Each star in Gaia's catalogue represents a point of light that has been shining on Earth throughout human history, influencing our art, mythology, and cultural development across civilizations. The mission also serves as a testament to our species' remarkable journey from prehistoric stargazers to cosmic cartographers. Our ancestors looked up at the night sky with wonder, creating stories and myths about the patterns they saw. Today, through Gaia, we're writing the true story of our galactic neighborhood, transforming those ancient points of light into real places with measured distances, motions, and histories. This understanding of our cosmic context arrives at a crucial time in human history. As we face global challenges on Earth, Gaia's perspective reminds us that we're all citizens of the same planet, sharing a tiny oasis in an incomprehensibly vast galaxy. The mission's data shows us that our sun is just one star among billions, yet it's also revealed the unique and precious nature of our cosmic home. By mapping our galactic family tree, Gaia isn't just helping us understand where we came from. It's helping us appreciate where we are and, potentially, where we might go. As we identify the paths of stars through space and time, we're also charting possible routes for humanity's future journey into the cosmos, creating a roadmap for our species' next great adventure among the stars. The implications of Gaia's vast data collection stretch far into humanity's future, offering unprecedented insights that will shape astronomical research for generations to come. The mission's precise measurements are not just illuminating our galaxy's past, they're providing a foundation for predicting and understanding cosmic events that will unfold over millions of years. One of the most dramatic future events Gaia's data helps us understand is the inevitable collision between our Milky Way and the Andromeda galaxy. By measuring the precise motions of stars in both galaxies, astronomers can now model this cosmic merger with extraordinary detail. We know that approximately 4.5 billion years from now, these two spiral galaxies will begin their gravitational dance, eventually merging into a single massive elliptical galaxy, sometimes dubbed Milky Way. Gaia's measurements are helping scientists predict exactly how this collision will unfold, including which regions of our galaxy might be most affected and how our solar system might fare during this spectacular event. The mission's data is revolutionizing our understanding of galactic evolution. By providing precise measurements of stellar positions, motions, and chemical compositions, Gaia is helping astronomers construct increasingly sophisticated models of how galaxies form, interact, and change over cosmic time. These models are particularly valuable for understanding the role of dark matter in galactic evolution, as the motions of stars reveal the invisible gravitational influence of this mysterious substance. This knowledge will be crucial for predicting the fate of not just our galaxy, but countless others throughout the universe. Perhaps most excitingly for humanity's future in space, Gaia's catalogue will serve as an invaluable resource for planning future interstellar exploration. The mission's precise stellar sensors is helping identify promising target stars for future missions, whether they be robotic probes or, in the more distant future, human expeditions. By understanding the positions, motions, and properties of nearby stars, scientists can identify those most likely to host potentially habitable planets or present interesting scientific opportunities. This information will be crucial for selecting targets for next-generation telescopes and possible interstellar missions like Breakthrough Starshot. The mission's data will also play a vital role in space navigation. As we venture further into the solar system and beyond, having precise stellar positions and motions will be essential for spacecraft navigation. Gaia's catalogue will serve as a three-dimensional roadmap of the galaxy, helping future missions plot their courses through space with unprecedented accuracy. Furthermore, Gaia's legacy will be instrumental in understanding stellar life cycles and evolution. By tracking changes in star positions and brightness over time, astronomers will better understand how different types of stars live and die. This knowledge is crucial for identifying potentially hazardous stellar events that could affect Earth, such as nearby supernovae or stellar flares from neighboring stars. The mission's data will also contribute to our understanding of fundamental physics. By providing precise measurements of stellar motions, Gaia is helping test Einstein's theory of general relativity on a galactic scale. Future analysis of this data might reveal subtle departures from current physical theories, potentially leading to new discoveries about the nature of gravity, dark matter, and dark energy. In the realm of planetary science, Gaia's measurements will continue to improve our understanding of asteroid trajectories and populations, contributing to planetary defense strategies and asteroid mining prospects. The mission's precise stellar catalogue serves as the essential reference frame for tracking these objects, helping us better protect Earth from potential impacts while identifying resources for future space exploration. Looking even further ahead, Gaia's data will serve as a crucial baseline for future astronomical missions and observations. By establishing precise positions and motions for billions of stars, the mission provides a reference point against which future changes can be measured. This will be invaluable for detecting long-term changes in stellar behavior and galactic structure that might only become apparent over decades or centuries. The technological advances developed for Gaia will also influence future space missions. The techniques and technologies pioneered by the mission, from its innovative scanning technique to its massive data processing capabilities, will inform the design of future space observatories, potentially leading to even more capable astronomical instruments in the coming decades. As we conclude our journey through the remarkable achievements of the Gaia mission, we find ourselves standing at the threshold of a new era in astronomical discovery. Every new data release from this extraordinary space observatory not only answers long-standing questions, but also unveils fresh mysteries that challenge our understanding of the cosmos. The mission embodies humanity's deepest aspirations, our desire to explore, to understand, and to place ourselves within the grand cosmic narrative. The impact of Gaia extends far beyond the scientific community. Its precise measurements and stunning revelations about our galaxy's structure and history remind us that we are part of something far greater than ourselves. When we look up at the night sky, we're no longer simply seeing points of light. Thanks to Gaia, we're seeing individual stars whose stories we now know, whose paths through space we can trace, and whose futures we can predict with unprecedented accuracy. This mission represents more than just a technological triumph. It symbolizes humanity's relentless pursuit of knowledge and our ability to transcend our earthly boundaries. Through Gaia's eyes, we've witnessed ancient galactic collisions, discovered stellar streams that tell tales of cosmic mergers, and mapped our galaxy with a precision that would have seemed impossible just a generation ago. Each new discovery adds another chapter to our understanding of the Milky Way's epic story, a story in which we all play a part. As we move forward, Gaia continues to monitor our galactic neighborhood, steadfastly collecting data that will benefit astronomers for generations to come. Its legacy will influence not just our scientific understanding, but also our cultural perception of our place in the universe. The mission reminds us that we are all travelers on a remarkable journey through space and time, inhabitants of a small planet in a vast and dynamic galaxy. For those captivated by these cosmic revelations, our exploration doesn't end here. Join our growing community of space enthusiasts by subscribing to Exploring the Universe. By becoming part of our audience, you'll gain regular access to the latest astronomical discoveries, in-depth analyses of space missions, and fascinating insights into the mysteries of our cosmos. Each week, we bring you new perspectives on the universe that challenge your imagination and expand your understanding of our cosmic environment. Remember, every like, share, and subscription helps us reach more people with the wonders of space exploration. By joining our community, you become part of a global conversation about our place in the cosmos. Together, we can continue to explore, learn, and marvel at the extraordinary universe we call home. Stay curious, keep looking up, and join us next week for another adventure in space exploration. The mysteries of the cosmos await, and we're just getting started.